Hey guys, welcome to GRO Mathematics and Statistics lessons. Today we are going to be talking about matrices and determinants, part 2. Okay, so in our part 1 video to matrices or on matrices, we discussed the definition of a matrix and we also talked about the order of a matrix. Still in that video, I talked about the location of elements in the matrix, but in this video, I'm going to begin with the general matrix, explaining the general matrix in the sense of locating elements in the matrix, and thereafter I shall focus on the types of matrices. So we have two objectives in this video. One is to talk about the general matrix in terms of locating elements in the general matrix, and then we shall talk about the types of matrices. So let's begin. Now, let's start with this. Let A be a matrix of order m by n. Okay, so if that is the case, the matrix A can be expressed in an expanded form as this. So if we were to write this matrix A in an expanded form, knowing fully well that the matrix is of order m by n, take note, the matrix is of order m by n means that matrix has m number of rows and n number of columns. Remember, matrices have what we call their orders, and the order of a matrix is a specification of the number of rows by columns found in that matrix. So all you have to do to specify the order of a matrix is to tell the number of rows by the number of columns found in the matrix. So what that means, if we are told that this matrix is of order m by n, it means it has m rows but n columns. Now, what I want to do in this video, to start the video, is to talk about what is called the general matrix. So the general matrix is what I'm trying to describe, and what the general matrix is all about is an abstract matrix. The general matrix is an abstract matrix in the sense that it does not contain specific values as its element. Rather, it is a matrix that contains abstract elements as representation of elements in the matrix. Okay, so let A be a matrix of order m by n. The matrix A can be expressed in an expanded form as what I'm going to do below, and I want you to follow me carefully. So I'm going to put A here. Remember, in our discussion on matrices and determinants part 1, that I told you matrices are represented with uppercase letters, so I'm using A in this case to represent my matrix. So I'm going to start from here. Okay, now if A represents the matrix, it is only proper and fair to use corresponding lowercase a's to represent the elements. So I'm going to start with writing A here. I'm going to continue A, 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 A. Now, I'm going to put ellipses here, and I'm going to tell you why. So I'm ending with A. I'm going to put ellipses here, and I'm going to end with A, okay? I'm going to write A, A, A. I'm going to put ellipses again, and I'm going to put A. I'm going to tell you why I'm doing that, but just follow me. I'm going to put ellipses again, vertical, and end with A. I'm going to do that for this case and end with A. I'm going to do that for this case and end with A. And I'm going to do that for this case and end with A. So this comes in here, okay? So that will close my bracket. Now, what am I trying to do? I'm trying to give a general representation of a matrix whose order is of order m by n, whose order is m by n, and we don't know in particular what m stands for. We don't know in particular what n stands for. We just know that there are m rows but n columns. So what we are going to do is this. Let me start with explaining this. This is the expanded form of the matrix A, and what I have done is to use, because we have uppercase A here, corresponding lowercase a's to represent the abstract elements in the matrix. Now, they are abstract because they are not exact values. They are not specific values of what the contents of A should be. So they are representing specific values. That's why they are abstract, okay? Now, in a matrix, we start talking about rows from the first horizontal space being, so this is row 1, this is row 2, this is row 3, take note. And because we don't know the total number of rows specifically, we will continue until we get to the last row. And according to the order of this matrix, this should be row M, okay? Now, on the other hand, you have this to be the first column. So we start mentioning rows from the top. So rows go from top to bottom, okay? Rows go from top to bottom. That's how rows progress. Now, on the other hand, you have these to be columns, okay? These are columns. So the first column is column 1. Why? That is because columns go from left to right, okay? So this is column 2, this is column 2, this will be column 3, and this, because it will continue, we will continue counting because we don't in this matrix know the specific number of columns. So we are going to call this column n, okay? So that is column n. Now, let's go back into the matrix. Now, we start counting the location or identifying the location of a matrix from the topmost left element. So this number here is the topmost left element. And in a matrix, we start with that element, the topmost left element. So what is the location of this element? You will notice that this element finds itself in row 1, but column 1. So we are going to put here row 1, column 1. So the 1, 1 there stands for the fact that the element finds itself in row 1, column 1. The second element here finds itself in row 1, as you can see, but in column 2. The third element finds itself in row 1, but you can see in column 3. So this last element here finds itself in row 1. I'm going to put 1, but notice it is in column n. So I'm going to put here 1n. Now, coming over to this element, you will notice it finds itself in row 2. So this is row 2, column 1, because it is in row 1. This is row 2, column 2. This is row 2, column 3, okay? And this is row 2, column n, okay? If you go to the third space, horizontal space, you will notice this element finds itself in row 3, but in column 1. This one in row 3, but column 2. This is in row 3, but column 3. And this is in row 3, but column n, okay? Now, if you go down here, that counting will continue. Now, why am I using ellipses horizontal ellipses and vertical ellipses. It is to show that the counting continues until we get to the last column in this case, and it is also to show that the counting continues until we get to the last row. And the reason why we are using ellipses again is because we do not know specifically how many rows are in this matrix and how many columns. So we were told it is just m by n, and m is not a number, neither is n a number. So we are using abstract elements. So this counting continues along the row until you get to the last row, and in the last row is row m. So this is row m colon 1, this is row m colon 2. This element finds itself in row m but colon 2. This is in row m colon 3, and this will be row m but colon n. Okay, so this representation of a matrix is the expanded form of this matrix. Now, you could choose to write a matrix also. Now, even as this matrix is in its expanded form, you can call this matrix a general. You can call this matrix a general m by n matrix. Okay? You can call it a general m by n matrix. Now, so this is an expanded form for the general m by n matrix. If I chose to write the abbreviated or shortened notation of A, of the matrix A, then I could then we could use the notation below. Okay, in that case, I could easily write A is a matrix having abstract elements A, I, J. Okay, now if you don't want to use this notation, which is the expanded notation, you can use this notation, which is an abbreviated notation or shortened notation. Now, in this notation, note what I am doing. I will write the matrix A, I will put the matrix here, I will put the order of the matrix. A m by n equals Aij, a matrix containing elements Aij, and I will now specify here where I runs from 1, 2, 3, 2. Now, take note, I represents the number of rows, and in this matrix, because the matrix is of order m by n, telling us that it has m rows, I will be from 1 to m, and j will be from 1 to n. So when you use this notation for representing an abstract matrix, then it means that you are representing a matrix in its abbreviated form or shortened form. Okay, now, so it is very simple to use. You write the matrix, you write its order as a subscript, then you now write you put the bracket, and then inside the bracket you put the abstract element A. If this were to be B, you may be putting a small letter B here, and then as a subscript you put Ij, where I stands for the row number, and J stands for the column number. And take note, because the matrix is of order 3 m by n, then it means that I will proceed from 1 to m, and J will proceed from 1 to n, because n is the number of columns. Now, let me quickly give an instance or example of these two. So as an example, let's quickly do this. Let's call it example 1. So my example 1 says, write the matrices A 3 by 2, B 4 by 1 and C 3 by 3 in their expanded and shortened notation. Okay, now take note, this is more or less a demand to write the abstract matrices or the general matrices of these ones, A, B, and C. So if you were asked to do this, all you have to do for the short, let's start with the first matrix, A 3 by 2. So I'm going to write this matrix in its expanded form. So what you're going to do is do this. Now this matrix has how many rows? 3 rows. So there will be 1, 2, 3 horizontal spaces. How many columns does it have? 1 and 2. Okay? So there are 3 rows in this matrix. There are 3 rows, but 2 columns. Column 1 and column 2. Now I'm doing this to guide you in solving the problem. So this would now be me writing A, because now I know the number of A's that should be in each column. A. Oh, this shouldn't be here because there are just 2 columns. So this will be A. Okay, so there are 3 rows, 1, 2, 3, but just 2 columns, 1 and 2. Now this element will be 1, 1 because it finds itself in row 1, column 1. This will be 1, 2 because of a similar reason. Row 1, column 2, row 1, column 2. That's why it is A12. This one will be row 2, column 1. So this will be 2, 1. The second will be row 2, column 2. So this will be 2, 2. This will be row 3, column 1. And this will be row 3, column 2. So this will give the expanded form of this matrix. Now if you come to the corresponding abbreviated form for this, then you would have A written as, that is, A will be written as A 3 by 2 equals, you simply bring this Aij, okay, for I equals 1, 2, and 3, being the number of rows you have, and J taking values from 1 to 2. Okay, so that will be the shorthand or shortened or abbreviated notation of this matrix corresponding to this. Now if you go to question number 2, you are going to have B41 equals, now there are 4 rows in this matrix but 1 column, so this is a column matrix. So this will be B, 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 and B along 4 rows, row 1, row 2, row 3, and row 4. Okay, now you don't need to write these row 1, row 2, row 3, and row 4 that I'm writing. I'm only using this to explain, okay? In the problem you just solve. Now I'm only using this to illustrate. So this will now be B1 because it finds itself in row 1, column 1. This one will be B1 and B2 because it finds itself in row 2, but this will be 1 because it is in column 1. This will be B31 because it is in row 3 but column 1. There is just 1 column. Okay, this will be B41. Now, moving from there, you would have the corresponding shorthand notation of this matrix to be B41 equals, you put a small b and ij, where I will take values from 1, 2, 3 to 4, and j will just be 1, meaning that there are 4 rows in this matrix and just 1 column. I hope you understand that. So you should be able at the end of this video to write the abstract matrix or the general matrix carrying its either in its expanded form or shorthand form. Okay, now let's go to number 3. So for number 3, we were asked to represent the matrix this. We are asked to represent the general matrix C. So this is number 3 in both expanded and shorthand notation. So I'm going to write 3 by 3 here, and this will be small c, small c, small c for row 1, small c, small c, small c for row 2, and c, c, c for row 3. Okay, now this will be 1, 1, this will be 1, 2, because it is in row 1 colon 2. This will be 1, 3, row 1 colon 3. Note that this matrix is of order 3 by 3. So I've written 3 rows and 3 columns. Column 1, column 2, and column 3. Okay, so this will be 2, 1, this will be 2, 2, 2, 3, for the same reason as what I've been explaining so far. This will be 3, 1, 3, 2, and this will be 3, 3. Okay, so this will be the expanded form of this matrix. But if we come over here, this will be the corresponding abbreviated form. So all you have to do is just put Cij, okay, because it is uppercase C, this will be lowercase c, and I will take values from 1 to 3, while j will take values from 1 to 3. So that is an explanation on that. Now, if you were to write the general square matrix, there's something, okay, as we shall see subsequently, the general square matrix. When we get into types of matrix, you would know what this means, but let me use it to explain. Okay, so if you have the general square matrix as a matrix that has equal number of rows and columns, okay, then if you were to write B, a matrix P by Q, then you would write this, especially when, in this case, P, the general square matrix, if P equals Q, results. Okay, so if it happens that P equals Q, the number of rows equals the number of columns, then the general square matrix will result from that. So you would have here B, B, and B, the first 3 elements, mention them and continue to the last. You have B, 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 the first 3, then go to the last. You have B, B, and B, the first 3 elements of that row, then you go to the last. On the other hand, you have mentioned the first 3 here, ellipses, the first 3 ellipses, then the last, the first 3 ellipses, and then the last, and this will continue till you get to this point. Now, this will be 1, 1, 1, 2, 1, 3. This will be 1, P. This will be 2, 1, 2, 2, 2, 3. Then this will be 2, P. Now, take note, if P is equal to Q, then I could just as well write P by P. Okay? So, this will be B31, B32, B33, up to B3P. This will be B, P1, P2, P3, and this will be P. Instead of writing PQ, it will be B, PP. Now, whenever you see that this is a square matrix because it has equal number of rows and columns in the general form, you can now put this. Okay? So, that will be our representation of what is called the general square matrix. So it is a matrix that has equal number of rows and columns. So let us now move ahead into the next discussion in this lesson. So what is our next discussion in this lesson? Our next discussion in this lesson is types of matrices. Types of matrices. So I'm going to start quickly with type number 1. Okay? There are several types of matrices. Let me mention them. We have the null matrix. The null matrix. Okay? So we have also the colon matrix. We have also what is called the row matrix. Number 4, we have what is called the square matrix, like I mentioned earlier. Number 5, we have what is called the diagonal matrix. The diagonal matrix. Number 6, we have what is called the identity matrix. The identity matrix. Number 7, we have what is called, after the identity matrix, we have what is called, or what we can call, triangular matrices. Okay? We have what is called triangular matrices. So we shall be looking at all of them. Okay? We shall be looking at all of them. Now, let us quickly look at the first one. Let's start with the first one, the null matrix. So what is a null matrix? A null matrix, to start with, a null matrix is a matrix whose elements are all zeros. Okay? A null matrix is a matrix whose elements are all zeros. Point number 2 to note about it, apart from its definition, is that a null matrix can be of any order. Okay, it can be 2 by 3, it can be 4 by 5, it can be this, it can be that. So a null matrix is a matrix whose elements are all zeros, and that is what makes it a null matrix. So examples of this matrix are, so I could write a matrix A, 0, 0, 0. This would be a null matrix. B, I could write a matrix 0, 0, 0. This will be a null matrix. I could write a matrix this 0, 0, 0, 0. This will be a null matrix. I could write another matrix D having 0, 0, 0, 0, 0, 0. This is a null matrix. I could have another matrix E having 0, 0, 0, 0, 0, 0, 0, 0, 0. This is a null matrix. These are all examples of null matrices. All it takes to be a null matrix is to have all your elements as being zeros. Okay? Now let's quickly go to the next type of matrix. Okay? Let's go to the next type of matrix. The next type of matrix we are going to talk about is the colon matrix. So the colon matrix. The colon matrix. Now, the colon matrix is a matrix having only one column. Okay? It's a matrix having only one column. So you can, if you don't want to define it that way, we could say let C be a matrix. Then if C is a colon matrix, if C is a colon matrix, then if C is a column matrix, then C is of order, C will be of order m by 1. That means we can write C m by 1 as this. Remember our abbreviated notation? Cij, I equals 1, 2, 3 to m, and j equals 1. Notice that in this matrix, there is just one column, but a number of rows, more than one, okay? So what we mean is that a matrix is a column matrix if it has only one column. So that is not difficult. Examples of column matrices. So what are examples of column matrix? Now take note. Let me put this here for you to remember. Column matrices are also called column vectors. Okay? So if you don't want to call it a column matrix, you can also call it a column vector. So let us see some examples of column matrices. A 0, 0, 0 is a column matrix even as it is a row matrix or a zero matrix. B equals 1, 4, 3 is a column matrix. C 1, 2 is a column matrix. D 1, 5, 3, 2 is a column matrix. Now take note of this. This matrix is of order 3 by 1. Notice this matrix is of order 3 by 1. This matrix is of order 2 by 1. This matrix is of order 4 by 1. Notice in all of them there is just one column, one column, one column. So all it takes for a matrix to be a column matrix is that it must have just one column. Okay? So, and that brings me to matrix number 3, the row matrix. The row matrix. So, when is a matrix a row matrix? A row matrix is a matrix having only one row. Okay? So let R be a row matrix. Let the matrix R, I'm using the matrix R to represent a row matrix in this case. So if R is a row matrix, then R is of order m or 1 by n. Okay? If we call R a row matrix, then it is of order 1 by n. Why? There is one row, but n number of columns. Okay? We have just one row, but n columns. Now, if you wanted to write out R in abbreviated notation, then we will write it as 1 by n equals Rij, I equals 1, j equals 1, 2, 3 to n. So this is a row matrix. Okay, take note. Now, if you want to consider another name for a row matrix, take note, a row matrix may be called a row vector. Okay, it may be called a row vector. And that brings me to examples on row matrices. So let's see examples of row matrices. I could take 1, 4, 3, 2. Notice it has just one row. I could take another matrix B equals 0 and 2. This is a row matrix. I could take another matrix C that contains 1, 5, 6, 3. This is a row matrix. I could take another matrix D that contains 1, 2, 1, and this will be a row matrix. I could take a matrix E that has 4, 5, 6, 3, 9, 2. This is a row matrix. Now take note, please, everyone. Notice I'm not putting a comma. So because it is written in this form does not mean you should put a comma after each of them. Let them be, but just give them space, okay? So these are all examples of row matrices. So a row matrix is also called a row vector, and a row matrix is a matrix whose elements in the rows are just, you have just one row, but you can have a good number of columns, okay? So what makes the row matrix is that it must have just one row. Now, let's move on from that explanation to the next type of matrix. The next type of matrix to describe here is the square matrix, okay? The square matrix. So that's number 4, the square matrix. So when is a matrix a square matrix? I'm going to write here, a square matrix is a matrix whose number of rows is equal to its number of columns. So any matrix whose number of rows is equal to its number of columns is a square matrix. So let's put it this way. Let M be a square matrix. Then we can say M is of order M by M, or N by N. Now, why am I doing this? Take note, for a general matrix of order M by N, take note, this matrix would only become a square matrix. It will only become a square matrix. I'm going to put here not square, and I'm going to put here square. So under what condition will a matrix of order M by N become a square matrix? It is only going to happen if M is equal to N. And in this case, M will now be N. So you can write in place of N, M, or you can write in place of N, you can write this. So if it happens that the number of rows becomes equal to the number of columns, then it becomes a square matrix. So these will now be square matrices, okay? So a matrix whose number of rows is equal to its number of columns is a square matrix. Take note, it's as simple as that. So if you want to write a square matrix M in shorthand notation, we could, that is of order M by N, we can write it as this. Ij, where I takes value from 1, 2, 3 to M, and J also takes value from 1, 2, 3 to M. Okay? So good examples of square matrices. Examples of square matrices are A equals 5, 6, 2, 3. This is a square matrix 2 by 2, you will notice. The next one, B equals 3, 4, 6, 1, 2, 5, 8, 9, 3. This is a square matrix. Notice it is of order 3 by 3. If you move on from there to C, C is of order 3, 1, 2, 5, 6, 7, 8, 9, 1, 0, 4, 2, minus 1, 1, 3, and 5. This is a square matrix. It is of order 4 by 4. So you can call a square matrix, if you don't want to call it a matrix of order n by n, you can call it, I could have called this an n square matrix. I could call this an m square matrix. Sorry, an n square matrix. Okay, I could call this a 2 square matrix. I could call this a 3 square matrix, and I could also call this a 4 square matrix. Either you write it in this form or in this form. Okay, so that's for a square matrix. It is not difficult to understand. Now let's move over to the next matrix, being the diagonal matrix. The diagonal matrix. The diagonal matrix. So now, before we go into discussions on the diagonal matrix, take note, there are certain things I'm going to talk about. So I'm going to start with talking about what we call the principal diagonal. Okay? Now, the principal diagonal of a square matrix is a diagonal that is drawn from the topmost left element in the matrix to the bottommost right element. So I want you to take note of that. Now, another name for the principal diagonal, that is, if you don't want to call it the principal diagonal, you can call it, another name for the principal diagonal will be the leading diagonal. The leading diagonal. Or you can call it the main diagonal. Or you can even call it the primary diagonal. Okay, so the principal diagonal of a square matrix is this diagonal, this one over here. So let me call this 3, 2, 1, 4, 5, 6, 8, 9, 3, 1, 0, 6, 4, 5, 9, 2. This diagonal that moves from this element down to this element is called the principal diagonal. Now, notice it is a diagonal that moves from the topmost left element down to the bottommost right element. So, notice that this is the topmost left element of the square matrix. This is the bottommost right element of the square matrix. This diagonal that is drawn from the topmost left element down to the bottommost right element is called the principal diagonal. Another name for the principal diagonal is leading diagonal. If you don't want to call it leading diagonal, you can call it main diagonal. If you don't want to call it main diagonal, you can call it primary diagonal. Okay? So that is what we call the principal diagonal. Okay? So the principal diagonal of a square matrix is a diagonal that is drawn from the topmost left element, this one, to the bottommost right element. Okay, this one. So this diagonal drawn from this to this is called the bottommost right element. It's called the principal diagonal. Sorry. Now take note, the reason why I am explaining the principal diagonal is because we have to define the diagonal matrix. Now, for us to define the diagonal matrix requires a good knowledge of what the principal diagonal is. Okay, so let's move on. Now I'm going to bring this over here. So let's go to the next thing. The next thing I want to talk about is still under diagonal matrices. I want to talk about the auxiliary diagonal. So let me start with saying that the auxiliary diagonal is that diagonal in a square matrix. Okay, so it is that diagonal in a square matrix that is drawn from the bottommost left element to the topmost right element. So unlike the principal diagonal that is drawn from the topmost left element to the bottommost right element, this one is drawn from the bottommost left element to the topmost right element. Okay, now what other names do we call the auxiliary diagonal? Auxiliary diagonals are also called secondary diagonal. Okay, they are also called secondary diagonal, trailing diagonal. So if you don't call the auxiliary diagonal a secondary diagonal, you can also call it a trailing diagonal. Okay, so these are names you could call the auxiliary diagonal. And if I have a matrix like this, 3, 2, 1, 6, 8, 9, 4, 5, 7, 8, 2, 3, and 1, 1, 6, 2, then what we call the auxiliary diagonal is this. Now, notice that it moves from this element here, which happens to be, it moves from this element, which happens to be the bottommost left element, to this element, the topmost right element. Okay, so the auxiliary diagonal, also known as the secondary diagonal, also known as the trailing diagonal, is that diagonal that is drawn from the bottommost left element, this one here, to the topmost right element. Okay, so please don't forget that. Now, that being said about the auxiliary and the principal diagonal, let us now go into the diagonal matrix. Now, the diagonal matrix can now be defined. The diagonal matrix can now be defined as a matrix that is a square matrix having elements along its principal diagonal, as non-zero elements, but elements along its of its principal diagonal as zeros. Okay, so what this means is simple. What we call a diagonal matrix is a matrix that has elements along its principal diagonal as 0 elements, but every other element in that matrix is a 0. It has non-zero elements, and every other element in the matrix is 0. Okay, let me show you what that means. So now if I put up a matrix 4, 6, 2, and 1. Now take note, this is the principal diagonal of this matrix. If this matrix must be a diagonal matrix, take note, it must be a square matrix. Okay, so diagonal matrices are square matrices to start with. They are square matrices that have elements along their principal diagonal as non-zeros. So you will notice that this is 4, this is 6, this is 2, this is 1. But the other elements of the matrix will be zeros. Every other element in this matrix will have to be a 0 if this must be a diagonal matrix. Now, let me use this medium to explain something. These elements here, all these elements that find themselves along the principal diagonal are called on-diagonal elements. They are called on-diagonal elements, while the elements that are away from the principal diagonal are called, that is all these elements, all of them here, are called off-diagonal elements. Off-diagonal elements. Likewise, these ones are also off-diagonal elements. So you can see now, based on this idea, you can even redefine a diagonal matrix to be a matrix, that is a square matrix rather, a square matrix whose on-diagonal elements are not zeros, but whose off-diagonal elements are all zeros. Okay, so if a matrix is a diagonal matrix, then its off-diagonal elements must be zeros, but its on-diagonal elements must not be zeros. Okay, now let's take an example of the diagonal matrix. Let's take examples of the diagonal matrix. So notice A equals 2, 4, this is a diagonal matrix because elements along this principal diagonal are not zeros, but elements of its principal diagonal are zeros. This is also a diagonal matrix, 1, 5, 0, 0. This is a diagonal matrix. Again, notice, not zeros. These are the principal diagonal elements. They are not zeros, but the off-diagonal elements are zeros. These are the off-diagonal elements. They are zeros. Off-diagonal elements are zeros. Okay? Now, if we take one more example, you will notice 4, 0, 0, 0, 0, 5, 0, 0, 1, 2, 0, 0, 3, 0, and 0, 0, 0, 1. This is also a diagonal matrix. Now, what three things would you notice about these matrices? Number one, they are all square matrices. The three examples I've just given, all of them are square matrices. What that means is that for these matrices to be diagonal matrix, they must all be square matrices, number one. Number two, you will notice that their principal diagonal elements are not zeros. Number three, notice that their off diagonal elements are all zeros. So these are the three conditions it takes for a matrix to be a diagonal matrix. Now that brings me to the identity matrix. Okay. Now the identity matrix can be defined as a matrix whose on-diagonal elements, let me even adjust this a little bit. The identity matrix must be a diagonal matrix. Okay, so you can define it as a diagonal matrix whose on-diagonal elements must be ones. That's all. Any diagonal matrix whose on-diagonal elements are ones is an identity matrix. Or you can define an identity matrix as a square matrix having its on-diagonal elements as ones, but its off-diagonal elements as zeros. That will make an identity matrix. Okay, now we usually use an identity matrix is denoted with uppercase I. So we usually use I to represent an identity matrix. So examples of identity matrices are A equals 1 0 0 1, it's an identity matrix. B equals 1 1 0 0 0 0 0 0 is an identity matrix. So this is a 2 by 2 identity matrix. This is a 3 by 3 identity matrix. Now note, you could just simply use I to represent this. You could use I instead of A to represent that matrix. So I could write here this and call it 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 0 0 1. Okay, so this will be a 4 by 4 identity matrix. Okay, so in shorthand notation, if I was to represent an identity matrix, or in a general expanded notation, if I was to represent an n by n identity matrix, I would simply write this to be, let's say a matrix A is an identity matrix. I could write this to be A 1 1. Of course, this is 1, or let me put this rather as 1. This will be 1. This will be 1 up to, okay, this will be 0. This will be 0. This will be 0. This will be 1. These are zeros. This will be 1. This will be 0 up to 0. This will be 0. Now, this will be for n columns, and it will go down up to 0. This will go down 0. This will be 1 up to 0, and this will be 0. This will be 0, and the last will be 1 for n rows and n columns. Okay, so you can write an n by n general identity matrix. Now, So that being said, let's go to the last discussion. And my last discussion is on the triangular matrix. So what is a triangular matrix? So I'm going to start this with saying that a triangular matrix may be of two types. One, it could be an upper triangular matrix, or it could be a lower triangular matrix. Okay, so now an upper triangular matrix is a matrix that is a square matrix rather. An upper triangular matrix is a square matrix whose elements on and above the principal diagonal are non-zeros, but whose elements below the principal diagonal are zeros. So what that means is that examples of triangular matrices will be these. Any matrix that has this feature is a triangular matrix. So similarly, this is also a triangular matrix. Now, why are these examples of triangular matrices? Now, look at the structure. You would see a triangular structure, of course. Now, note this is an upper triangular matrix because all the elements on the principal diagonal and above the principal diagonal are all not zeros. But every element below are zeros. Now, a lower triangular matrix is the reverse of this. Okay? It has all elements above the principal diagonal as zeros, but elements below as non-zeros. Okay, so an upper triangular matrix has elements above the principal diagonal and even on the principal diagonal as non-zeros, but those below are zeros. A lower triangular matrix has elements above the principal diagonal as zeros, but those below and on the principal diagonal are not zeros. So a good example of that would be this. So you have 3, 4, 5, 6, 2, 1, 0, 0, 0. This is a good example of a lower triangular matrix. Notice that every element above the principal diagonal are zeros. All the elements below are not zero. If I put up a matrix like this, 4, 1, 5, and 0. Notice again, this is a lower triangular matrix because the elements on the principal diagonal and below it are non-zeros, but the ones above are zeros. If I put up this 5, 6, 3, 2, 8, 9, 4, 5, 1, and 6, 0, 0, 0, 0, 0, 0. Notice this again. This is a good example of the lower triangular matrix. All the elements below and on the principal diagonal are not zeros, but every element above is 0. So I'm going to stop here in this video. Please like our video, subscribe to our channel, very important. For more content, subscribe to our channel, and then like our videos, share our videos, and I'll see you all in a bit. Thank you very much.